examples, while we're still kind of establishing this visual notation, this notion of how it is that we're actually defining these distributions. We'll come back to that application. Okay. Any questions before we jump in? So last time we were talking about the regressive levels. Questions about those? So one of the good questions that came up in office are already kind of like folded into the lecture, so it's not actually on this slide. So we'll move on to people. So goal number 2 is going to be kind of this picture of taking what we're doing here and applying it to a real world problem. So you'll be looking at the task of semantic segmentation and implementing an inference algorithm learning that kind of combines deep neural network, semantic convolutional neural network with a graphical model and training them both to solve this task of semantic segmentation. So for now, you guys are wrapping up Dagger for sync, and then we'll move on to that next task. Okay, so I have one more thing that I want to do. So there's one last thing that I could say about undergraduate graphical models, but there's sort of one more thing here that I really wanted to focus in on, which is that of pairwise Markov random fields. And it's just sort of a useful notion to have in mind while we're thinking about these particular types of models. And here, what we're really thinking about is essentially a particular kind of restriction on our definition of an undirected graphical model. So we're going to call this pairwise Markov random field. That's going to be really annoying. So there's like the webcam has crashed, which happened once before. This is why you should never self-record your own course. So the mic looks like it's frustrating.
It is. It's really noisy. You can't make out any words.
Okay. So how many people do we have online? That's the other question. Are there actually people online?
Yeah, there are 9.
And the computers are like full too. I can't even tell them that I just come to class. Okay, so I'm trying to think of whether I should derail class for 5 minutes and try to figure this out. Or online section. Okay, so I think I'm gonna give you all 5 minutes, and what I'd actually like for you to do in this 5 minutes that's not a complete waste is talk to someone who you do not know in this class. Find out what program they're in, and what their sort of interests are when it comes to machine learning. And what I hope will come out of these short conversations is that now you will know at least one more person in this class. So when you're starting to think about projects, which are going to be group projects, you'll know at least one more person here that might have sort of different interests from say the friends that you came into this class with. So this is the advantage of being here in person. So hopefully they don't maybe know what I'm saying. So go ahead and take just a couple minutes to specifically meet someone new here and swap ideas. Just if you already have ideas around the kinds of applications of machine learning infrastructure creation that you're interested in, while taking a second to see if we can fix the broken drivers. Okay, so I just unplugged it, and it like dropped off and then came back in. So I wonder if it was using. I might have just switched the microphone or something. All right. Well, now I'm not even sure. So
Yeah, the audio is better.
okay. All right, we're good then.
I'll try and grab your attention in the first like 30 seconds if it's not, if
Okay.
it's still not working. But I think that sounded like it fixed it.
Okay. Okay, so I hope you met someone new, and hopefully they weren't exactly like you. That would have been really disappointing if you guys had like exactly the same interests and there was no cross-pollination of ideas. But at the same time, if you were sort of two sides of the same coin and have similar ideas, maybe you're actually more likely to end up working together. So I think either way that works out well. I think we have likely fixed the online section issues. So we're going to jump back into things here, and we'll just plow through. And worst case, I think at this point, if things are still failing, I'll figure out a way to like re-record. Okay, so a pairwise Markov random field just makes a specific restriction on a graphical model, specifically an undirected graphical model. So if we had one that consisted of, say, 4 variables like this, then we might have undirected edges connecting them like so. And the general MRF formulation would assume that we're working with the maximal cliques. So if I asked you all for the probability of x1, x2, up to x4, what would that be? What are the terms that define this?
Energy function product for x1, x2, x4, and x2, x5.
Yeah, so there's going to be some potential function for x1, x2, and x4, and then some other term for x2, x3, and x4. And what?
Divided
By the partition function, exactly. So we divide this whole thing by z. Great, so here's a different way of actually defining a probability distribution based on this graph. And specifically, this is the pairwise MRF way of doing it. In this case, what we do is we restrict to edge potentials. Okay, so what this looks like is we define the joint probability over these same random variables based on potentials that only look at where there are edges. So we would have a 5 for x1, x2, sorry, these are psi. A psi for x2 and x3. For, what else do we have? x2, x1 and x4. And x2 and x4. Miss any? Maybe x3 and x4. I think that's all the edges. There should be 1, 2, 3, 4, 5 edges and 5 terms here. And then we divide this whole thing again by z to make sure it sums to 1. Okay. So these are not equivalent definitions of the joint distribution, right? The original sort of standard MRF formulation is actually more general. Okay? So this is sort of a restriction on our original definition. We could still take
Did I get this right? So the terms that involve 2, 3, and 4 would be this one, this one, this one. And we could say that the product of those 3 that involve 2, 3, and 4, if you take that product, you get back one of the 2 terms. And then if you take the product of the remaining 2 terms, you get back the first potential function. So more generally, what we can say is, if you want a general pairwise MRF, then you can define that to be a joint distribution over some random variables x, where this is defined to be a product from, say, I equals 1 to t. Let's assume there's t random variables. And for each one, we're going to have a unary potential function for that random variable. And then we're going to have another product over pairs ij in a set E. And for each of those, we'll have a potential function over xi, xj, where here, that set that these ij pairs are coming from is something called E, and that E is an edge set. So when we define it this way, we're essentially saying that there are sort of 2 pieces of the puzzle. The first is this term in brackets, which we refer to as unary potentials. And then the second is the second term in brackets, which we refer to as edge potentials. And so we have these 2 terms, and you can see that in the example that I gave you, I just left out all of the unary potentials, and I only gave you the edge potentials. So this is another way that we could actually specify kind of a specific form for a Markov random field.
So, are the 2 potential functions, the functional form is same, or is it like different?
So, yeah, this is a good question. So, what is the actual form of these things? Well, that's a question that I'm sort of pushing off purposefully. So, in some sense, at this point, all we care is that there's some functions that give us back some numbers. Okay, what are they actually going to come from? Well, they might be tables. Okay, if they're tables, then they might start to feel a lot like the Bayesian networks that we were defining with tabular or conditional probability tables. Okay, if they're not tables, maybe they're functions of some features and some parameters. In that case, they could actually feel a lot like a linear model, except one that kind of decomposes. What you guys are eventually going to be working with is a setting where these little scores are actually coming from a neural network. And so there's lots of different ways that we're going to be able to get these functions, and that will have implications for how we actually train the thing. But for now, they're just, I think the best way to think of them at this moment is just think of them in terms of a table of numbers. And the question will just be, where does that table come from? Okay, so I'm not going to go into these. There's lots of sort of famous Markov random fields, like the Ising model, the hot field network, the Potts model. These are sort of specific types of parameterizations of those functions. And we'll be looking at something kind of akin to a Potts model for image segmentation on homework 2. Okay, so what I want to move to is a discussion of factor graphs. And this is going to allow us to capture both directed graphical models, like Bayesian networks, and also the undirected graphical models that we've been talking about, these Markov random fields. Okay, so remember we kind of talked about how you could imagine having, say, a joint probability distribution over some variables x, and you can imagine drawing samples from that joint probability distribution. Now, we have various graphical models that could specify a joint distribution. And we're going to see how we could come up with a factor graph representation like this one from those existing definitions. Okay, so these are the factor graphs that we've actually seen so far. Let's actually figure out what it is they're doing. Okay. So factors, so a factor graph is going to consist, again, of variables and edges. But now there's going to be a new kind of node. And they're going to be these little black boxes that we're going to call factors. And so if you think carefully, we actually have a bipartite graph here. It's hard to see it, but imagine if I grabbed all of those little black boxes and pulled them up to the top of the slide. What would be left on the bottom is all of the variables. Now keep all those edges connected, and you could imagine further that there wouldn't be any edges between variables and variables, or between factors and factors. Okay, so it would be a bipartite graph because each of the factor variables connects only to variables, and each of the variables connects only to factors. And so when we say that factors have local opinions, now this starts to give shape to some of the ideas that we've been talking about in this abstract notion of these potential functions. We can start to think of potential functions as factors in a joint probability distribution where they express some preference locally for the values of the variables that they're touching. So what we're going to build here is a correspondence directly between factors and potential functions, and factors and conditional probability tables, where potential functions are coming from undirected graphical models and conditional probability tables are coming from directed or Bayesian networks. Okay. So here you could imagine that maybe we're trying to do part of speech tagging again. And so the factors that connect, say, a tag variable and a word variable are going to be a big table. And for each possible value of the tag, like a verb, a noun, a preposition, or a determiner, they're going to have one separate row. And they're going to have one column for each possible value of the word. Time flies away. Everything down to zebra. And so we could see that here, so flies has a high score for being a verb or a noun, but it has a really, really low score for being a preposition or a determiner. So this particular factor is expressing an opinion that if the x1 variable is a determiner and w1 is the word flies, it's going to be really upset because it's given a really low score, like 0.2. Okay. Similarly, we're going to have these edge factors where the edge factors are actually also expressing local opinions, but about a pair of tags, say x1 and x2. Okay. So this particular factor gives a really high score to a verb followed by noun, a score of 6, and also a noun followed by a verb, a score of 8. Okay, so in this particular case, we chose to kind of reuse some of the factors at different positions, right? This factor has the same tabular values as the second one next to it. Okay. So now, if we want to define a joint probability distribution over both the tags and the words, then we can do this just by picking out the corresponding values in the factors, right? These are just potential functions in an undirected graphical model. And here we say, okay, for a particular assignment to the variables, we've now filled in the variables with their values. When this is noun and this is time, we pick out 4. And for noun followed by verb, we pick out 8. For verb followed by preposition, we pick out 3. Verb flies, 5. And we start multiplying all those scores together. And what we get is this product of these local opinions. Okay? So you can think of this joint probability distribution as sort of happiest when its individual factors are locally happy with the assignment. And then, of course, if we want this to actually give us back a valid probability distribution, where if we had summed over all of the possible assignments to these variables, we would have gotten something unnormalized. So we need this term 1 over z to make sure that it is normalized properly. Okay, so a Markov random field is just going to be this joint distribution over tags and words. And the individual factors aren't necessarily probabilities. Okay, so in a Bayesian network, the only change is that, well, one, we got rid of the little factor tables, the little factors in the picture, and we switched to directed arrows. And two, we changed from unnormalized tables to normalized tables. And how they're normalized is actually important, right? So you can see in these two top tables that the rows are normalized, not the columns. Okay? And so what they're defining is a conditional probability, the probability of verb following noun, or column following row. And similarly here, these are probability of word given tag, and so the columns, the other way around. The rows, again, sum up to 1. Okay. And now, because each of these conditional probability tables is locally normalized, we're ensured that we have a valid probability distribution, even without z. Put another way, the partition function for a Bayesian network is always 1. Okay? And so we don't need this global normalization term on a Bayesian network. Okay. Okay, so here's our Markov random field again, and we can make a small change to it and obtain what's called a conditional random field. So to get a conditional random field, we're going to assume now that we're no longer defining this joint. So both of the Markov random field and Bayesian network are joint distributions over tags and words. A conditional random field is now going to define a distribution over tags given words. Okay. So the actual form of the distribution is now conditioned on a specific sentence. So what changes here? Not that much. Okay, so notice that this little factor is now just touching a tag, right? Because the sentence is essentially given, it's conditioned on. So the possible values that this factor can take are just 4 different values for the different values that the tag could take on. Okay, where did those values come from? Well, if you look at what I did, I actually just said, well, if the sentence we're conditioning on is time flies like an arrow, then we're just going to snip out this column from that table, and then this column from this table, and those will give us the CRF factors. That's where these came from. Okay, so this is sort of feeling like everything on this slide looks exactly like everything on this slide. But there's something subtly different about the two. Does anyone see what is actually different when we're defining these two probabilities? I mean, sure, one's conditional, one's joint, but should they have this? Do they have the same value? The answer is going to be no. Here's a joint probability. We're using some set of numbers. Okay. So this is going to be a joint probability, and it's going to be a different value, right? This number here is going to be a different number than this number. But I just said that all the numbers in the tables are exactly the same. So what's different? That's a good question. So there is actually a difference in independence assumption here, specifically centered around x. But that doesn't yet account for, but those same conditional independencies that existed in the Markov random field are also going to exist in this particular conditional random field because I took the numbers directly from the Markov random field. So there's something else that is going to change to account for the difference in these two probabilities.
The partition function.
Exactly. What is different about the partition function?
So there was a different sum, different amplitude sum together.
Exactly. So the partition function for the Markov random field has to sum over every possible assignment to tags and words, not just for the sentence time flies like an arrow, but for every possible sentence. Or well, I guess maybe every possible sentence of length 5. Here, we're only summing over the possible tags for this specific sentence. So the actual number of sum-ins in the conditional random field is dramatically less. And the term 1 over z is going to be much smaller. Okay. So both the factors and this partition function z are now specific to the sentence. And that's what gets us a conditional random field. Okay, so factor graphs are, we're going to spend a lot more time talking about conditional random fields, but we're going to do so in the context of training when we're actually thinking about how we define these potential functions. So factor graphs can be used to describe Markov random fields, conditional random fields, Bayesian networks, and inference is going to treat all of these interchangeably so that you can convert your model to a factor graph first and then just run inference on it. Okay. Any questions? Okay. So there have been, for quite a long time, strategies for exact inference in these sorts of models. One of them is belief propagation. We're going to talk about this one. The junction tree algorithm is another one, which tends to be in sort of less prominent use at the moment in the world, and so we won't actually focus as much on it. But it's good to know that it's there. Okay, so what we want to think about is this factor graph notation and how we can move from factor graph notation to a general purpose inference algorithm. Okay, so what we have in a factor graph are variables and factors, where factors are really just potential functions. And so the joint distribution defined by a factor graph looks very similar to what we were doing with an undirected graph, an undirected graphical model. The only real change is that now, instead of these potential functions being a product over, say, all possible cliques in the graph, they're just a product over all of the factors in the graph. So the factors are now making explicit what was sort of implicit in the undirected graphical model. In the undirected graphical model, you have to actually look at the graph and figure out which are the maximal cliques of this graph. I mean, it's a little graph problem, and you actually had to solve it. Here, the actual graph itself, because these factors are already present, encodes what the things we are multiplying together are. Okay. So let's actually look at an example of a factor graph here. So here we want to think about sort of a simple factor graph, and we'll do so in the context of a factor graph over binary variables. And so we'll just say this small example is going to have 3 binary variables, A, B, and C. And we'll say further that there's a factor connecting A and B. There's a factor just touching A, so you can shade these in. And there's a factor connecting A, B, and C all together. So we could actually label these factors. We could say, okay, this one that only touches A is psi A, and this is psi AB, and this is psi ABC. Okay. Where the subscript of the psi is just denoting, is just showing which of the actual variables it's touching. Okay, so now we can actually look at what these little potential tables hold. So opening them up, we can see that psi A is just a table over the possible values, little a, that the random variable A could take on. So little a, the value could be either, say, 0 or 1, because it's binary. And so psi A could take on values, say, 2, 7. And then we could have another table here showing psi AB. And that would be a table that ranges over 4 different values, so 0, 0, 0, 1, 1, 0, and 1, 1. And for each of the 4 different values of little a and little b, we could actually fill in the potential table, so it could be something like 4, 3, 6, and 2. Okay, so then we need one more table here, and the last table is going to be for the last factor, where we could say the last factor is going to range over all possible values of A, B, and C. And here, that's going to be values like 0, 0, 0, 0, 0, 1, 0, 1, 0. And then let's just elide a few of them, and we'll jump down to 1, 1, 1. And so the actual values that we'll look at are just going to be some 6, 2, 1, and 5. Again, where we're kind of aligning the ones in between. Just take a second. Okay. So each of these tables is representing one of the little factors in the graph. And we can now kind of conceptualize how they're coming together to form a joint probability distribution. So specifically, what we're doing is we're defining, say, the probability of random variable A equaling little a, B equaling little b, and C equaling little c. So this joint distribution is defining, say, a probability mass function B of A, B, C. And what we're doing here is, under the factor graph model, saying that that takes value 1 over z times psi a of little a, psi ab of little ab, and psi abc of little abc. And then here we could also say that the last 3 terms, the psi a term, the psi ab term, and then the psi abc term, are going to define for us some score, where the score is just going to be some function of A, B, and C. And so with that, then we can sort of compactly define Z to just be a sum over the possible values of A, little b, and little c for the score of ABC. So this is just sort of a more compact way of writing out Z, where S of ABC is actually these three terms multiplied together. Okay, so we could actually think of this joint distribution as itself coming from some big table. Okay, what does that big table look like? Well, it's going to have to consider the possible values of the random variables, A, B, and C. And those will be like 0, 0, 0, 0, 0, 1, 0, 1, 0. And then again, like the third factor, I'm going to kind of elide a couple rows and jump down to 1, 1, 1. And what we could do with this table representation is now we could actually write out all of the different components. So psi A is going to take on values according to the values in the first column. Okay, so how would I fill in the column psi A when we're looking at all the values of A, B, C? What would those values be?
Only the value of A.
Yeah, so what is the value of psi A for the first row?
2.
Yeah, 2. And then 2 again. 2 again. And it's not 7 until that last row where we get A equal to 1. Okay, so we can do this for each of the factors, right? So now we're going to have, sorry, this should be a capital A, psi AB here. And there, we're going to look at the values of A and B. So A and B are 0, 0 in the first row. So we consult our little table. So that means psi of AB would be contributing 4. And then here, there's 0, 0 again. So it'll contribute 4. And then it's going to be 0, 1. So that would be 3. And then at the bottom row, it's 1, 1. So that's going to be 2. Okay. And then psi AB, C, well, this one is the one that we didn't actually even write them all out, so we can just copy that down. 6, 2, 1, and 5. Where again, we're aligning everything in between. Okay, so now we can do something interesting, which is we can now say that the score that we were computing, that score is actually the product of the three values from each row. So the score of the first thing is 2 times 4 times 6, which is something like, what, 48? And then 2 times 4 times 2, 16. And then 2 times 3 times 1, 6. And then 7 times 2 times 5, 70. Okay, so now we have a score for each possible configuration of the random variables. And further, we could also think about having another column, which is the joint probability for all of these. How do we get the joint probability?
Divided by the score. No, we add the scores and then divide it by the product of all the.
Yeah, so we need Z if we want to compute the probability. So what is Z? It's just the sum of all of these scores in this column, plus all the ones that I left out, right? So there's a whole bunch right in here. And if we added all of these up, they would equal the value of Z here. Once we have Z, now we can come back to that definition for the probability and say, this is just 48 divided by whatever Z is. And this is 16 divided by whatever Z is, 6 divided by whatever Z is, and 70 divided by whatever Z is. Okay? So, okay. This feels a little bit like, okay, I get it. It's a table. We can expand it out. That's nice. But this is also exposing some really important computational implications going ahead. Okay. So specifically, notice that in order to compute the probability, we have to compute something for every row. But if all we want is the score, then we only need to look at a single row. Right? The score only depends on the values of its own row. Right? It's only the probability that depends on z, which needs to compute everything. So this starts to expose why computing that partition function is hard. And then as well, why even evaluating the probability for one of these models is hard. Okay, so what we're seeing here is that factors are actually just tensors. And so depending on what or how many variables the factor is actually touching, it's a different size tensor, right? So if it's just touching one variable, then the factor is a vector, which is a one-dimensional tensor. If it's touching two variables, then it's a matrix, which is a two-dimensional tensor. If it's touching three variables, like this one, then it's a three-dimensional tensor. And so indexing into it requires the values of all three variables. Okay, so now finally we get to one of the punchlines, which is that we can convert a Bayesian network to a factor graph. And it's really straightforward. To do that conversion, each conditional and marginal distribution in the directed graphical model becomes a factor. Right? So remember that for the Bayesian network, there was one term in the joint probability distribution for each variable. And the term was, how was it defined? It was the probability of that variable conditioned on its parents. So for this little Bayesian network up there, we would have had 6 separate terms, one for each variable, conditioned on its parents. And so we would take the same set of 6 random variables, but now we would add in factors that show what those conditional probability tables were actually involving. So for the first variable, which had no parents, it's a unary factor that only touches this variable. Okay. But for a more interesting variable like this one that had 3 parents, the factor has to connect to each of the 3 parents plus the variable itself. So the actual values for this factor are going to come from the conditional probability table that was, if this is, say, variable A, and this was B, C, and D, the values for this factor are given by that conditional probability P of A given B, C, D. Oops, D. Okay. So what we're looking at for the directed graphical model converted to a factor graph is just a sort of a one-for-one of those terms. For the undirected graphical model, each of the individual maximal cliques would become a factor. Okay. So here, the way I did it was not just the maximal cliques, but also the sort of non-maximal cliques. Okay. So in this case, we can have say here is a clique, and it also happens to be a maximal clique, and so it gets converted to a factor between those two variables. Okay. Over here, between these 3 variables, we have a maximal clique, and so we get back this factor that touches all 3 of them. Okay. Okay, so we can take this further and start to talk about both directed and undirected trees, where we can see that any undirected tree can actually be converted to a directed tree by choosing a root node and then directing all the edges away from that root. And then a directed tree and the corresponding undirected tree actually end up making the same conditional independence assumptions. And the parameterizations are mostly the same, right? So here's the directed tree. Okay, let's start there, where we have some variable that is the root, and then we have a bunch of other edges, a set E of edges, and we have conditional probabilities for each of those edges in the tree. Converting that to an undirected model, we would get back potential functions that look kind of like a pairwise MRF. Except that there's a further restriction, which is that we define the actual potential functions to be their locally normalized counterparts from the Bayesian network, which gives us that the partition function is going to be 1, and then also the unary potentials for everything except the root are also going to be 1. Okay, so here's a bunch of little examples. So this is a factor graph over 5 random variables. And so we could take each of the probability terms in it and map them to some factor term. And the result, and then if we just think about this factor representation, we could draw out the corresponding graph, and that would be this one, where we have a factor for each of the terms in this product. If we had an undirected example, like this example 2, where it's already a product of 3 factors, then the conversion to the factor graph is really straightforward. The interesting bit is that if instead we had parameterized this undirected model in terms of its maximal clique, then that would actually give rise to a different factor graph. Okay. So this is actually why I dislike undirected graphical models. Yeah, I know that it takes less ink to draw the undirected graphical model, and it's easier if you're trying to actually put one together in Tixie and get it into your PDF paper. But the factor graph is much more specific. It's actually encoding which of these 2 factorizations you actually meant when you drew this particular factor graph. So essentially, the undirected graphical model is ambiguous.
Oh, so I was just going to ask about this. So you're saying that you can have 2 different parameterizations for the same graph. Would they yield the same outputs, or would they interpret it differently?
I guess the key point is that, so think about the actual numbers that you would encode in these tables, right? The way that you actually encode, so you can encode any representation that you have in this top graph, you could encode it in this one, right? So it's not that so this one is general enough that it can capture any encoding of that other factorization. But it's nice that the factor graph actually distinguishes which one of these you were really talking about. The other thing to keep in mind is that we're going to run inference on these things, and the number of variables that your factors are touching is actually going to have computational implications when you're running an inference algorithm. Yep.
Let's say just we are given the factor graph. From that, can we infer whether it came from an undirected graph or a directed graph? Can we go the other way?
You could. I think we usually don't even think about doing that, sort of because once you've converted to the factor graph, there's not. So you can easily go back to an undirected graphical model. The challenge is that you'd also need to know how the actual factors were parameterized to know whether it's even possible to get back a directed graphical model,
So basically, you have to know where it came from.
or how we actually define these factors, right? Like, if these factors don't actually admit a locally normalized model, like if they're all unnormalized factors, then we can't go back to a Bayesian network. Okay, so there's another interesting thing that happens here, which is that, so you can have these sort of tree-like structures in undirected graphical models that are not trees, right? This is not a tree, it has a cycle. But when you convert it to a factor graph, we get rid of the cycle. Okay. Similarly, with a Bayesian network, this is a polytree, and we can actually convert it to a factor graph, which is itself an undirected tree. So this is a polytree because it has multiple roots. Okay. So why do we like this? Well, there's lots of reasons, but one is that factor graphs can turn these tree-like structures to factor trees. And if your factor graph is a tree, this guarantees that when you run the belief propagation algorithm on it, you'll get a guaranteed correctness and essentially a usually efficient exact inference algorithm. Okay, so now let's talk exact inference. Okay, so remember, we kind of said that, there's a lot of stuff going on here. There's understanding what our data looks like. There's defining our models, which we just spent a lot of time on. We're going to come back to learning next time. And here I want to focus in on inference. So we said that there's a bunch of problems like marginal inference, computing the partition function, and map inference. And that the first two are sharp P hard and that map inference is NP hard. So I want to give a really simple solution to solving all these problems. Because conceptually, this one just is kind of nice. Okay, so we kept on thinking about taking samples from this joint distribution. Okay, so now let's actually suppose this is the joint distribution that we have. It's a factor graph. We actually know what the values of these tables are. And so let's imagine that you draw a sample from this distribution. And then another one, and another one, and another one, and another one, and another one, until you get a whole collection of these. And then you say, okay, now that I have a bunch of samples, I want to estimate a marginal probability. Okay, so what is a marginal probability? Maybe we should actually, maybe we should take a moment and remind you all what a marginal probability looks like for one of these factor graphs. Okay. So suppose what we had was, I'm going to give us a slightly more interesting factor graph here. It's going to look almost like the one that we just worked with, but we're going to add a couple variables. So it's going to have A, B, C, D, and also E. And again, we're going to have a factor between A and B. We'll have a factor connecting A, B, and C. We'll have a factor connecting C and D, one connecting B and D, and one connecting D and E, and one more hanging out with A. And so if we want to talk about a marginal probability, then one such marginal probability that we might care about is the probability of random variable A equaling value little a. So that's some probability mass function P of A. And to compute it, all we need to do is sum over all the possible values of A, all the possible values of B, C, D, and E for the joint of A, B, C, and D. Okay. We could also compute other marginal probabilities, like probability of B. And to do that, we would sum over a different collection, or a different subset of the variables, right? Everything except for B. So we'd sum over the values of A, C, D, and E, adding up all of the probabilities from the joint.
supposed to be open?
Oh, thanks. Yeah, so here, this is a joint over lots of things. We're supposed to feel like a lot. Okay, so we could also compute other interesting marginal probabilities. Like, for example, you might want to compute the probability of A, B, and C marginalizing over D and E. So that would require summing over the values of D and E for the joint. Okay. So these are all marginal probabilities, and the question is just, which variables are we marginalizing out? So here we say we marginalized out D and E. So I'll use this technical terminology, this notion of marginalizing out some variables to mean the variables that are there in our joint representation, but that we've gotten rid of by summing over them. Okay. All right, so now what we can think about is how would we compute marginals on this factor graph? You have a bunch of samples. Where could you get a marginal probability from? Yes. You can have more samples if you want, if it makes you feel better. Say I want the marginal probability of x1, summing over all of the other ones. How could I get it?
Make a table and then conditional probability table.
We could make a table. We'll do that in a minute, but you've got these samples sitting there. Can't someone put them to good use? Yeah.
So for x1, if you multiplying for n, we look at all the samples which has n in them, and we kind of count the number of times.
Yeah, we count the proportion of times that x1 took on value n, right? We could say that we could estimate the marginal, in this case, as 4/6 of the 4/6 of the time it was n, and 2/6 of the time it was v. Okay. All right, this feels like a pretty coarse estimate to the marginal, but now imagine that you didn't just take 6 samples, but that you took 10,000 samples. Okay. Now, suddenly, it's some proportion of the 10,000 samples that you took. You're counting up how many of those were nouns and how many of those were verbs. Okay. And so for the next variable, you could do the same thing. Well, 3 out of 6 times it was noun, and 3 out of 6 it was verb. Here, 4/6 preposition. Oh, okay, this one wasn't terribly interesting. It was just 100% determiner. And here, this one was 100% noun. Well, gosh, now it sort of feels a little silly, because, maybe there is actually like some verb use of arrow. Then, maybe it's just not like popular yet, but people are going to start using arrow as a verb, and it'll have some cool online meaning that all the kids think is great. And so maybe if we had more samples, we could actually find out that there is some small probability of it being a verb. Okay, so what if you feel uncomfortable with this solution? Because as it turns out, it's generally not easy to take samples from one of these factor graphs. Okay, sampling from one of these factor graphs is, in general, also an NP-hard problem. Okay, so if you had samples, great, you could estimate the marginals, but getting them is hard. Okay, so let's think instead about a very direct algorithm for computing something like a marginal probability, and that's going to be variable elimination. Okay, and this is sort of general exact inference for graphical models. Okay, so first step, take your BayesNet, your undirected graphical model, whatever it is, convert it to a factor graph. Okay, now proceed like this. we're going to have some specific graphical model here where we're going to suppose that the range of each xi is 0, 1, or 2. And so k equals 3 is the size of the range that the variable can take on. And the distribution factorizes like I've shown. So naively, we would compute the partition function as a sum over each of these variables, adding up p of x. Oops. This should be, see what my notation will be. Oh, okay, that's just a mistake in the slides. So this shouldn't be p of x, this should be s of x, right? This is the score of x, right? And what is the score of x? It's this thing. Okay. So the score is just the product of these psi terms. Okay. So we can represent, oh, I see what I was doing. Okay, so over here, yeah, okay. So we could represent this score table with 3 to the 5 entries in a giant table, right? And then if you wanted to add another column here, which was p of x, you could do that, and you could do that by adding up all of the entries in the s of x column and then dividing the score by that value. Okay. So the question is, can we do better? So the variable elimination algorithm is a cute trick, and what we're going to do is basically just capitalize on the actual factorization of this graph. And the whole trick here is that you need to realize that summations can move around. If you have a sequence of summations like this one over x1, x2, x3, x4, and x5, that x5, it's at the front, right? But we can muck with the order of operations here and actually slide this x5 summation all the way in, so long as the term that we're moving it past doesn't involve x5. Okay, so let me give you a quick example of this, because I think it's harder to see in that case. So suppose instead I had a summation over a variable x. Okay? And the terms in the summation were 6 times 7 times, oh, whoops, I shouldn't use that for times, huh? We'll use a different random variable. Suppose the summation was over y, and it was 6 times 7 times y. Does anyone feel uncomfortable with me just, sliding this summation in? Not at all. It's just 6 times 7 times the summation over y of y, right? Totally fine. Okay, so now let's jump back here. That's all we're doing, right? We're just saying that x5 is not involved in any of these first terms. The first time it appears is right here and right here. And so we can slide this thing all the way up to sit right in front of these last two terms. Okay. As soon as we've done that, now we can say, okay, if we wanted to, there's only 3 squared additions that are needed to marginalize out the variable x5. And we could actually make a little table corresponding to all of the work that would be done in order to marginalize out x5, right? So this little table is going to consist of the possible values of x4 and x5, and then all of the scores. Sorry, this p of x is wrong again. This is again s of x. Okay, for the values of x4 and x5. Okay. So now, what we can do is replace. So let's make this a little clearer. So this entry, these entries in these tables, we're going to call M5 of x4. And this is going to be the value summing over x5, whoops, or sorry, each of these is going to come from this term. So note that M5 of x4 is a function of x4, but it marginalizes out x5. It's not necessarily a probability, though. It's just another factor. But this time, the factor only depends on x4 because we've marginalized that out. Okay, so now, oh, here we go. It was already defined on that slide. So M5 of x4 is defined as a summation over x5 of this product term. And this thing takes 3 squared additions. Okay, but this doesn't solve anything because if we just expanded things out into the big table, we'd still have a 3 to the 4 entry table. Okay. So what we could do then is repeat this process over and over, each time sliding our summation out as far as we possibly can, and then collapsing down a term for each of those summations. Okay. So the first step, so each of these, so let's actually look at what each of these is doing. The first collapsing, so let's look at the first line here. So notice that we moved the summation for x5 as far to the right as we could. Then we moved the summation for x4 as far as we could, and x3 as far as we could. But then for x2, we couldn't actually move it anywhere because the first term involved x2. Okay. So our first step is going to be to collapse this whole thing into a single term. Okay. And then we're going to collapse this whole thing into a single term. And then this, and finally this. Okay, so the first collapsing requires 3 squared additions. Why is it 3 squared additions? See that?
Because it's 2 variables and both of them have 2 values.
Exactly. We defined the range for our variables to be 0, 1, or 2. And there's 2 variables involved here, x4 and x5. And so if we want to create the table is going to consist of 3 entries for the 3 possible values of x4. To fill in each of those table entries, we have to sum over the 3 values of x5. So that's 3 times 3. Okay, that's where we get our 3 squared. Okay, this next one, collapsing it, is going to involve 3 cubed additions because we have 3 squared table entries, and each one of them has to sum over x4. And then again, we get 3 cubed additions here, and 3 squared there. And then finally, 3 additions to get the partition function. Okay, so if we just create the giant table of the 3 to the 5th entries, and then add them all up to compute the partition function, we need 243 entries in the table and 243 additions. But variable elimination can do it in just 75 additions. So we can use this same trick to compute marginal probabilities. So you would just choose the variable elimination order such that whichever one you're trying to marginalize comes last. So you can see here, if we wanted the marginal probability for x1, we could use that same order as before, but we're not going to sum over x1. We're just going to return 1 over z times 2 of x1. Okay. So it's the same amount of work because we're still filling in the same table entries. Okay. So for, this is just the same statement we've made a bunch of times. Okay, so here's sort of the visual depiction of what's actually happening here. So the first term in the first row there corresponds to the yellow parts of the factor graph. And variable elimination, the reason we call it variable elimination, is basically just removing that part of the factor graph and replacing it with a new factor. That new factor is going to have a different name, though. It's not going to be called psi anything. It's going to be called M5, indicating that it was the new factor that we essentially got by marginalizing x5 out and putting in the resulting factor. Okay. So the first step of variable elimination here is just removing that part of the factor graph and replacing it with factor M5. Okay. The second step is going to take all of those terms. Well, that corresponds to x4, but also psi23, psi234, and M5. And it's going to replace it with another factor that's a function of x2 and x3. So that whole yellow part of the graph gets replaced with M4. Okay, so this would proceed all the way down, gradually replacing these things by marginalizing out little parts of the graph at a time. And the key thing that we're capitalizing on is that the only reason that we can move these summations in like that is because we know how the joint probability factorizes. Okay, so variable elimination for marginal inference is the actual input is the factor graph and the query variable, and then the output is the marginal distribution for the query variable. And so if you want to implement this thing, what you'd do is you'd actually run a breadth first search starting at that query variable to obtain some ordering on the rest of the nodes, a topological order. You'd then reverse that order, that would give you a reverse topological order, and you would eliminate each variable in that reversed ordering using algorithm 2. So algorithm 2 is just, how do we eliminate one variable? Well, the input is the variable to be eliminated, and the output is just the new factor graph with the variable marginalized out. Okay, so find the input and its neighboring factors and call this the eliminated set. That was the yellow stuff that we saw on the previous slides, the parts that you were about to eliminate. And you replace the eliminated set with a new factor where the neighbors of the new factor should be all of the neighbors of all the factors in the eliminated set. And the new factor should assign a score to each possible assignment of its neighboring variables. And said score should just be identical to the product of the factors that it's replacing, summing over the eliminated variable. Okay, so the same thing works for the partition function as we saw. Okay, so we're over time, so we're going to skip this last little exercise here, but it's kind of interesting to see how the computational complexity works out here. And so we'll actually pick up with this next time. And what we'll do next time is we'll actually look at another general exact inference algorithm called belief propagation, which is a message passing algorithm that can accomplish the same sort of thing, but even more efficiently if you want to compute many marginals at once. Okay, see you guys on Wednesday.
I have a question about the homework.